My project is over unanswered questions in cosmology. That is the phenomenon I'm discussing. And cosmology is the study of the cosmos, and cosmos is defined as the universe as a well-ordered thing. So I'm going to mainly be focusing on dark matter and dark energy. There are two big things, or big, they have, well, they're big things that we can't really see or measure in a way. That's why measurement will be so important to, learn about. We know they are there because of the things that we can't actually see and the effects that they have on actual matter, like the real matter we see. So that's how we know that they're there. We don't actually have a way to measure them. That's why they're considered dark, and that's, I guess, a pretty interesting thing because we can see the effects, but we can't see the thing. It's like suddenly seeing a baseball being thrown at the catcher, but not seeing the pitcher that's actually doing the throwing. So this video talks about dark matter. It actually explains it pretty well. And I'll be expanding on this for further understanding.
Ever had the feeling that there's something bigger out there, something you can't see? Well, there is. It's called dark matter. Dark matter is spread throughout space, engulfing the Milky Way and all other galaxies. It's 4 times more common in the universe than visible matter, yet we've never seen or directly observed it. So how do we know it's there? Because of gravity. A galaxy is like a giant merry-go-round that all the stars are riding. In order to stay on, each star has to hold on tight. That's where gravity comes in. Otherwise, it'll fly off into space. The problem is, the force of gravity from all the stars we can see isn't strong enough to hold galaxies together. All the stars should be flying off the edge of the merry-go-round, but they're not. It's as if some invisible rope is helping them hold on. Physicists believe that rope is the gravitational force from stuff we can't see, hence dark matter. And how do we know the speeds of stars in distant galaxies? The Doppler effect, which is why a police siren shifts to a lower pitch as the car passes, also works for light. That's how radar catches you speeding, and how astronomers measure the rotation of galaxies. So, we use what we can see to tell us about what we can't.
So this video makes some really good points. If you notice how it talks about the Doppler effect, so the Doppler effect is not focusing on dark matter, but on the real matter we can't see. So what it's doing is it's measuring what we can see, and from those measurements we can predict what would be needed to hold the galaxies together, like the merry-go-round. So we know, so of the visible stuff we can't see, we know it's not enough to hold the actual galaxy together. It's not enough mass to create the gravity that's holding the galaxies and preventing the stars from just spinning right off and leaving the galaxy. So that's how, I guess that plays a role. And then, as it said that there's a lot more dark matter than real matter, and actually, dark matter or real matter consists of about 4 to 5%, depending on the different measurements you'll use, of what's actually inside the galaxy and the universe as a whole. So it's only 4 or 5%. 20% of that is dark matter. 20 to 20, it's actually 20 to 25, depending on the different studies. And then 70% of that is dark energy, which is completely different from real matter and dark matter. It's also dark because we can't really see it, but we know it's there because of the effects that it's had. And one of the biggest effects that it's had is on the actual galaxies that were in the universe. And so what's happening is that the galaxies around the universe, they're expanding and they're moving further and further apart. The thing is, they're actually accelerating. So it's expanding faster and faster and faster and faster. So this is one of the coolest phenomena because we don't know what's actually causing the expansion. We would actually think they would not necessarily just slow down and decelerate, but they wouldn't continue to expand faster and faster. So dark energy is a pretty neat thing. This goes over some of the basic concepts and of what it does and how we've known it to exist. This came around the idea of dark energy in the late 90s about what it could do and what its properties are. And this kind of happened because we started to see that galaxies, after the Big Bang, galaxies were would expand, they, I guess, get further away from each other. What we expected, without knowing of the existence of dark energy, is that they would expand and then they'd start to slow down in a way because of the effects of gravity from different galaxies on each other, so they wouldn't expand as quickly anymore. They'd slow down in a way. But what we actually found is that they're actually speeding up. This phenomenon is pretty interesting because we don't know what's causing them to speed up. There's several predictions. Some of them include a modification of gravity's properties on the larger scale, and another thing would be this dark energy that's causing the accelerations. This video goes over some of the concepts, and I like the illustrations because they provide big key ideas of what it could actually mean in the large scale.
We've known for a long time that the universe is expanding. If you look at distant galaxies, they're moving away from us. And the more distant galaxies are moving away faster. So really, it's not just an explosion of galaxies away from us. All galaxies are moving away from all the other galaxies. Space itself is getting bigger. But you'd expect that the expansion of the universe is something that would slow down. These galaxies have gravity. They attract each other. So you would expect the expansion of the universe to diminish with time. So it was a big surprise in 1998 when we realized that the galaxies are actually speeding up. If you look at one galaxy, not only is it moving away from us, but tomorrow it will be moving away from us faster. This is what we call the acceleration of the universe. But we're not completely baffled. We have a good theoretical model handed down to us by Einstein. The idea that even empty space has energy, what we call vacuum energy or dark energy. And this vacuum energy pushes space itself. It causes distant galaxies to move away from us faster and faster. That's where the acceleration comes from. So theoretical cosmologists are trying to understand what could be going on. Is it really vacuum energy? Is it some variation of that? Or is it even a modification of Einstein's general relativity, our theory of gravity? If vacuum energy is the right answer, the universe will continue to expand, galaxies will move away from us, and the universe will gradually become a lonelier, darker, emptier place.
So what it talked about Einstein's theories and how Einstein might have been wrong is it was actually talking about how Einstein's properties of gravity and what he described gravity would do on larger scales and around us in space would actually be modified and actually change and account for some of the things that happen in the actual universe and how galaxies are getting further and further apart faster and faster every time. So this is one of the possible theories, and then the other is like the dark energy that's pushing them and causing them to accelerate. So that's probably one of the most interesting things, because this dark energy, we can't actually see or measure the amount of energy like we could, I guess, in another experiment that we might be able to do, like push a car and find the kinetic energy, the non-conservative work that's performed on the car. We can't really do that with things on such a large scale with energies we can't really measure in a way. We know that they're there because of the effects. We know that they're doing something. We don't know how to measure this something that they can exert on other things. We know that they're exerting the things, but not necessarily the amount that they're having to exert per unit, per se. And then we can take and measure the stuff that's happening on the large scale of the universe in the same way that we were able to use the Doppler effect to measure the spinning of galaxies and how the shift in color would be like the shift in, like the example said, like the police siren that goes by, how we hear it lower or higher depending on the distance and the speed and all that. So we would see different colors of a galaxy depending on the way it's spinning and the speed and how it's accelerating and changing. So that's how we measure one of the effects of the dark matter, the dark energy. And then that's how we know that it's spinning so fast that the stuff we can't see can't actually hold the galaxy together. There has to be the dark matter, like I said earlier. And it's actually a pretty cool thing because it's something we can't really, I guess, touch or feel in the same way that I can touch or grab my TV. And it's fascinating. fascinating. Some science fiction type stuff has expanded on what this dark matter or antimatter could do, and the thing is, we don't know if it's right or if it's wrong. We have predictions, but we haven't been able to test this dark matter or antimatter because we just don't know how to grasp it, which is interesting. It plays such a bigger role in the real matter we can see because the dark matter is just so much more. It's like I said, some measurements are from 4 to 5% of real matter we can see, and 20 to 25% of matter that we can't see. So it's the dark matter, and then there's the dark energy, which accounts for 70% of things. So it's like having a big empty room that's not really empty. It's got something in it, things you just don't know that it's. We know that it's there. We just don't know how to just take a picture of it in a way. Then another thing that there's other unanswered questions that there are in cosmology is like, for example, uniform temperatures in the universe. We would think that it'd be more or less a uniform temperature all around, since it'd be able to transfer, reach eventually a point of equilibrium where it'd be it's a uniform temperature, but that's not the case. It's actually uneven in certain parts. And then another question is the fate of the universe. What's actually going to happen? Is it going to continue to grow or expand so fast that using this dark energy, or will it eventually flatline out and just continue to exist? And another big theory is the Big Crunch, which would mean that so galaxy grabbed and or the universe started to, after the singularity and the Big Bang, it exploded and it started to expand. It reached a certain point. It reached the maximum of its expansion, and then started all to collapse slowly and come together. It just started to crunch, and it's called the Big Crunch because of what would happen. It all just come together back again into sort of a singularity, and the cycle might start over. It might not. That's a big question we have out there. We're just not sure what's really going to happen. And then another thing is the monopole problem. So these monopoles are like tiny magnets that should have been created according to many theories and different ideas by prominent physicists. These monopoles should be created, and they should be like tiny magnets that should, I guess, pass through us every second. I'm talking about molecularly tiny. And many theories and equations need these and produce these in the outcome. The thing is, they've never been observed, so we're not sure how this will work. One theory that might account for these three things is the inflation field theory, but it's a whole different story for another time. But some of these things are pretty neat. Dark matter, dark energy, and how it affects the world we live in, the universe we're in, how it's accelerating, expanding, and how we can see so little of what's actually there. It's baffling, impressive.